Greetings and welcome, friends. We're talking today about conditional probability. Good stuff. We've actually seen glimpses of this concept in some of the kneecap questions. Let me tell you about what this means. It is the probability of an event under the condition, conditional, that some preceding event occurred. Bam. So that's conditional probability. I think we saw this once again with the black vans problem, where we said, what is the probability that the vehicle is black given that it was a van? So the given was kind of like it narrowed down our initial possibilities, where it's like, all right, if I already knew this, then what did that tell me about the probability? So our formula for it goes this way. P of A, and then it's got this line, and then B. And that's read, by the way, as P, the probability of A given event B, right, occurred, is what that means, I guess. You just read that as P of A given B. And what that's going to equal is you find the probability of A and B occurring. All right, so like a both situation. And you put that over the probability of B. And there's one stipulation that P of B cannot equal 0. And why would you suspect that's the case? Well, wait, what was your reasoning? Well, but sometimes we do have events that are certain to not occur. But why do we not like B not having that possibility based on this formula? Yeah, well, if we divide by 0, it would be undefined. So there's no such thing as dividing by 0, sadly. So that's the idea, all right? The formula takes a little while. Well, it's not difficult to apply, but the understanding of why the formula works, I don't know, it takes a little bit of time for it to sink in. But overall, I think this concept is somewhat intuitive. Let's say I'm flipping 2 coins. All right. What is the probability of flipping 2 coins? Oh, flipping 2 heads. There, I was about to say, I was like, that's something redundant. Flipping 2 heads given that at least one head is flipped. Well, let's actually draw out a sample space of this situation. What are some possible outcomes for using H for heads, T for tails? I could have what when flipping 2 coins? I could have what, H and H. I could have HT. And then, yeah. Right, so there's 4 possibilities here. All right. So according to our formula, let's see, what do I want to find out? I want to find out what is the probability of A and B occurring. So what's the probability of 2 heads and at least 1 head? So How many of these have both of those occurring? Just one of them, right? So a 1 out of 4 shot. And then what's the other portion I have to figure out? I have to find the probability of B, the given fact. So what's the probability of at least one head? Yep. So let's see, there's these 3 situations. And I get, yeah, 3 out of 4, exactly. Okay? So according to the formula, I'm supposed to divide these things, right? Thinking ahead. So we'll have 1/4 divided by 3/4. It's the same as multiplying by the reciprocal, so that's 1/4 multiplied by 4/3. Those 4's can cross cancel, and I'll get 1/3 is the probability of getting 2 heads, given I know that I'm going to have at least one. Now, another way I could have canceled this out, I want to point out, is that the 4th and the 4th would have canceled out. So I actually end up really only being interested in these numerators here. But also, does 1/3 make sense? Look at my sample space. If I knew that I had this purple, if this purple space was my reduced sample space, there are 3 outcomes. And how many of those have 2 heads? 1 out of the 3.
But it was saying what is the probability of 2 heads, flipping 2 heads, given that 1 head is flipped.
So it's basically just asking for the probability of 2 heads. But you have to eliminate tails, and you have to take into account so that, like, I don't know, you eliminate the tails so that you have only the ones that have 1 head, so that you can make the denominator and
Yeah. Yeah. So it's just like that van problem. What is the probability that the vehicle is black, given that we already knew it was a van? So I was only interested in the vans, and then I just figured out which of the vans were black, right? So I can exclude any of the ones that didn't have the given fact initially, is the idea. So, all right. Now, let's look at another example. All right, let's say I roll a 1d12. You guys know what a d12 is. It's a 12-sided die, right? So let's find the probability. Actually, I'll just write it probability style. The probability that the number is a multiple of 4, mult of 4, given that I knew that it was even. Now, you might intuitively be able to answer this question already, just thinking about it. But let's see. So what does that mean I need to do? I want to find the probability of both occurring, right? Mult 4 and even, right? So I guess I can write out my numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Or I should have just counted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you watched PBS back in the late 80s, early 90s, you would know how to count to 12 that way, just so you know. Side note, cultural, time, chronological significance there. So how many, let's see, let's figure out first of all, how many of these are multiples of 4 and even? 4 is a multiple of 4 and even. 8 is a multiple of 4 and even. And 12 is a multiple of 4 and even. So the probability of both of those occurring are 3 out of 12. And now I got to figure out what's the probability of my given fact, right? So how many of these are just straight up even? Well, 2 is, 4 is, 6 is, 8 is, 10 is, and 12 is. Right? Or I could have divided 12 by 2, realized, 6 is what I get, and that it starts with an odd, ends with an even, so 6 of them had to be even, right? Blah, blah, blah. So 6 out of 12. And it might make sense not to reduce these in this case, because I'm going to end up dividing them in a moment. So let's see, 3/12 over 6/12. And if we're fancy, I can just be like, those 12s are going to cancel out. So I'll get 3/6. I hate that word. 6ths. And 3 goes into 3 once, into 6 twice. And I get a half. That's my answer.
Wait, why wouldn't you reduce it?
Well, you could. I'll show you.
Then when I reduce it,
3/12 is 1/4. 6/12 is 1/2. So then, doing it that way, I would have had 1/4 divided by 1/2. I couldn't cancel out necessarily. Well, I guess if you're fancy, multiply by the reciprocal. Multiply by 2 over 1. 2 and 4 partially cancel. It's the reciprocal of the denominator is what it'd have to be. So now looking at this, where does this 3 associate with my sample set? Yeah, those are the green ones. And then where does the 6 relate to my sample set? Right, all of the purple ones. So I just want to point out that notice 3 out of the 6 were multiples of 4, right? So this makes sense intuitively, and then the formula takes a little while to be like, oh, I probably wouldn't have realized that weird formula, but it happens to work out every time, right? So I like you being able to kind of like at least check your answer visually, but I wouldn't want you to be able to derive your answer visually only, because it's worth being able to calculate these formulas if for some reason, say we had some crazy huge sample space and writing it out by hand wouldn't make sense. But I do like the fact that it seems to line up and make sense, right? So let's see, let's do one more problem. Let's see. I'll scroll over to the right. Why not? My near infinite virtual space to work with. All right, let's find. So I'm drawing cards from a deck. So deck 52. Right? Find the probability. We draw an ace, given I know that I've drawn a heart. So, first thing I need to do is find what's the probability of ace and heart. So how many cards are both aces and hearts? 1 out of 52, right? There's only one ace of hearts. And then I need to find out what's the probability of just getting a heart. 13 out of 52. So the probability of an ace, given I already knew I had hearts, right? Like if I had a deck of cards and I was like, all right, pick a card. Well, wait, time out. Let me just take the hearts out of this deck and now pick a card. So you already know that there's just hearts in this deck. You would be able to figure out the probability that you'd get the ace of hearts. Right? We'd be able to cancel. It's going to be 1 out of 13. Let's see. So, I mean, it's not too crazy, I don't think. Right? Not too crazy. I don't think it's that bad. So there's our 3 examples. One thing I want to point out, there is a slight modification to the formula where in our second example, I could have done a simpler version of it. Let's see, here's our second example. In this case, if I drew a Venn diagram, let's see. All right, I do want to point out that the one formula works every time, so that's why you don't have to know this technique. All right, and if I drew the even numbers, right, what would the Venn diagram look like if I wanted to draw where the multiples of 4 existed? Could I draw this if this was mult 4? No, because there's never a multiple of 4 that isn't even, right? So it's going to look like an egg with its yolk, right? So multiples of 4 are going to be a complete subset of that. So if that occurs, it turns out that the formula P of A given B can just be simplified to being the probability of A divided by the probability of B. But I don't think it's even worth your time memorizing it. But let's just verify that this works. What is the probability of A in this case? How many multiples of 4 are there if I didn't have this? What's just the probability of multiple of 4? It still was going to be 3, the green ones, out of the 12. So it ends up being the same thing. All they're trying to do is make a formula where, oh, it actually wasn't that complicated to find the probability of both occurring, because if it was a multiple of 4, it by default was also going to be an even. All right. So I don't think you have to memorize that formula. The general one works in all cases anyway, and I'll just let you, float off of that. So thanks for watching, Internet friends. I hope you have a great day.